Okay, this is our makeup video because of my absence on Tuesday. And if you see this video, you should be able to do all the homework twos, which is due in a week. So we'll go over this material again to some degree on Tuesday. But I just wanted to make sure, again, you had this stuff ready so you can work on the homework over the weekend. Okay, so what we're trying to do here, like I talked about in class earlier today, was try to come up with ways to make predictions in games. So we came up with two ideas. The first one was this idea of domination. So remember, we say that for a given person, strategy A strongly dominates strategy B if the person's payoff from strategy A is greater than their payoff from strategy B, regardless of what everyone else is. So the idea is, if strategy A strongly dominates strategy B, then strategy B will never be played. We can make that prediction. Okay. And then the second thing we came up with is this idea of weak domination. So it's sort of the same as strong domination, except it's weaker. So the yellow parts are the parts which are different. We say that strategy A weakly dominates strategy B if the person's payoff from strategy A is at least so her payoff from strategy B, regardless of what everyone else does, and sometimes greater. So in other words, strategy A weakly dominates strategy B if the payoff is always at least as great and sometimes greater. Okay, so let's do some examples. We did a little bit of this this morning in class. Let's do this again. Okay, so here we have a two-person example. Do you see any domination? So let's just check. For example, for person 1, does A dominate B strongly or weakly? So for A to strongly dominate B for person 1, it must be the case that the payoff from A must be greater than the payoff from B no matter what person 2 does. So let's just check. If person 1 plays A and person 2 plays A, well, we have 8 versus 4, yes, so in this case 1A is better than 1B, right? But we have 0 versus 5, so 0 is less than 5. So in other words, it's not the case that 1A is always better than 1B, right? Sometimes 1A is worse. So in other words, 1A does not strongly dominate 1B. Okay, how about, let's see, let's do 2A and 2B. Does 2A strongly dominate 2B? For 2A to strongly dominate 2B, you have to check whether this number 1 is bigger than 0, which is true, but 5 is less than 6. So in other words, it's not the case that these numbers are all bigger than this. So remember that when person 2, you're comparing the second number, the blue numbers. Okay, so what do we have here? I think what we have is weak domination. We have person 1, strategy 1B, weakly dominates 1C. So let's see how this works. 4 is greater than 1. This is a tie. 5 and 5 is a tie. And 7 is greater than 6. Okay, so remember the definitions from we had last time, right? A strategy A weakly dominates strategy B if your payoff from strategy A is at least your payoff from strategy B and sometimes greater. So again, 4 is bigger than 1. It's a tie here. 7 is bigger than 6. So we have 1B weakly dominates 1C. And it weakly dominates because of this tie here. Like if this 5 were like a 6, then it would be strong domination. But it's weak domination because, again, 4 is bigger than 1. There's this tie here, and 7 is bigger than 6. And the idea is that 1B weakly dominates 1C. 1B is always at least as good as 1C, and sometimes better. Okay. So there's no strong domination here, but we have the case that 1B weakly dominates 1C. Okay. Let's move on. How about this person? This is a 3-person case. Let's check for person 1. Say, does 1A strongly or weakly dominate 1B? Well, if 1A were to strongly dominate 1B, then the number here must be bigger than this, etc., but we don't have that, right? 0 is less than 5. So 1A does not strongly dominate 1B. Similarly, 1B doesn't strongly dominate 1A, right? So 5 is bigger than 0, but 0 is less than 5. So it's not the case that 1B is always better than 1A, or 1A is always better than 1B. Okay, how about person 2? I think we have 2B weakly, 2B weakly dominates 2A. How do I know? Well, person 2 is comparing this 6 with this 4, right? So if she plays 2B, she'll get 6. If she plays 2A, she'll get 4. Okay. So 6 is bigger than 4. 8 is bigger than 3. 1 is bigger than 0. And here we have a tie. 4 is at least as big as 4. Yeah, so 2B weakly dominates 2A. In other words, playing 2B is always at least as good as playing 2A and sometimes better. Okay, so 2B weakly dominates 2A. let's just check person 3. If we do person 3's domination, we're checking this number with this. So this 0 with this 6, this 0 with this 0, etc. So for example, for person 3, does 3a weakly dominate 3b? Well, 0 is less than 6, so no, right? How about does 3b weakly dominate 3a? No, because 0 is less than 6. So it's not the case that 3a is always at least as good as 3b, and vice versa. Okay? So again, in this case, 2b weakly dominates 2a. Okay, another example. Oh, so we can iteratively eliminate weakly dominated strategies too. So this is, let's use this as a review. We first eliminate some strategies and then see if we can eliminate some more, etc. in an iterative process. This method is called the iterative elimination of weakly dominated strategies. So again, iterative means you just keep on doing it over and over again. Let's look at this example. Okay, let's see. I think we said that, 1b weakly dominates 1c, again, because 4 is better than 1. There's a tie here. 7 is bigger than 6. 1b weakly dominates 1c. So, therefore, we can eliminate 1c, I think. Right? 1c is weakly dominated by 1b. Okay, now in this game, do we have any domination? I think, let's check. Let's see. Yeah, 2c weakly dominates 2a, right? Because 3 is bigger than 1. And there's a tie here. So in other words, in this smaller game, 2c is always at least as good as 2a and sometimes better. Okay. So now in this game, we have 2c weakly dominates 2a. And therefore we can eliminate 2a. Okay, now about here. What kind of domination do we have? Well, now in this smaller game, I think 5 is bigger than 0, 7 is bigger than 2. So in other words, for person 1, playing B is always better than A. And the name for that is strong domination. So person 1, B is always better than A. 5 is bigger than 0, 7 is bigger than 2. 1B strongly dominates 1A. So therefore we're going to get rid of 1A. And then finally we have this. Person 2 now is the only person who's choosing. 1's now sort of stuck at B. That's what he's going to do. Okay, so now person 2 is choosing between B and C. 6 is bigger than 5, so 2B in the smaller game strongly dominates 2C. And we can eliminate 2C. Okay. Some people ask me, like, in this game, why are we eliminating this? Because isn't 7 bigger than 5, right? But the key thing to remember is that here person 1 isn't choosing anymore, right? The only person who chooses here is person 2. 2 chooses between B and C. So 2 only cares about the blue numbers, right? Those are 2's payoffs. Person 2 doesn't care about the red numbers at all. Okay, so person 1, of course, would like person 2 to play C. Person 2 doesn't care. Person 2 only cares about the blue numbers. So person 2 chooses the 6 over the 5. In other words, B over C. Okay, so this is our final prediction. 1 will play B and 2 will play B also. Okay, so in our original game, we ended up predicting that 1 will play B and 2 plays B. Okay? So, iterative elimination of strongly and weakly dominated strategies is a good way to make a prediction in the game. So far, it's the only way we know, and it's not bad at all. Any possible drawbacks, and we talked about this a little bit this morning. Turns out that there is a drawback. For iterative elimination of weakly dominated strategies, sometimes the order of elimination matters. There is an element of arbitrariness. So people asked about this morning. Yes, it's possible that the answer might depend on the order in a kind of arbitrary way. This is true for weakly dominated strategies. For strongly dominated strategies, however, you don't have to worry about it. The order of elimination doesn't matter, and there is no arbitrariness. In other words, eliminating strongly dominated strategies is, so to speak, always safe. You don't have to worry about it. You can do it any time, you can save it for later, whatever. It doesn't matter when you do it. Iterative elimination of strongly dominated strategies is always safe. Okay, so let me do this example, which illustrates why weak domination can be kind of arbitrary. Okay, so here person 1 has 3 strategies, person 2 has 2. Let's see, so let's try to solve this by iterative elimination of weakly and strongly dominated strategies. Okay, so one way to do it is to say, well, 1A strongly dominates 1B, right? Because 8 is bigger than 4, 8 is bigger than 4. So therefore, we're going to get rid of 1B. Now, in this game, we have now person 2 2A now weakly dominates 2B, right? Because we have this tie, and 2 is bigger than 0, right? So we can eliminate 2B, because 2A weakly dominates 2B. So we eliminate that. Then finally we have for person 1, 8 is bigger than 4, so therefore 1A strongly dominates 1C. And we have this left. So starting from original game, the prediction is 1 will play A, and 2 will play A also. Okay? That was one order of elimination. Again, just to go over it again, we started from this game. Okay, we had 1A strongly dominates 1B. We eliminate that. Given that, 2A now weakly dominates 2B. Now given this, 1A strongly dominates 1C, and we're left with this. Okay. As you might have sort of expected, there's another way of doing this, right? We can say 1A strongly dominates 1C instead, okay, and eliminate that. Now in this game, 2B weakly dominates 2A, right, because it's a tie here and 2 is bigger than 0. So then we can get rid of 2A. And now, for person 1, 8 is bigger than 4, so 1A strongly dominates 1B. We have this. So this is another prediction which kind of, well, it's a different prediction from the first one. Remember, in the first order of elimination, we ended up with 1A and 2A, and now we end up with 1A and 2B. Okay, it's a different prediction. And you might say, well, the reason why this is a problem is because, in the first order we allowed 1A to eliminate 1B. In the next case, we had allowed 1A to eliminate 1C. What we should have done is allow 1A to eliminate both 1B and 1C at the same time. So what happens if we do that? We can say that 1A strongly dominates 1B and 1C. If we do that, we're left with this. There's no more weak domination, so we can't eliminate anymore. And our prediction is this or this. Okay. So this simply shows us that this example shows us that since we did allow weak domination, okay, it's possible for the order to matter in an arbitrary way. So when you do the homework, you'll see that too. Sometimes you'll have examples where, depending on the order of elimination, you'll get a different result. So it's just good to be aware of that. Again, so depending on the order of elimination, we get 3 different predictions. Okay, so when you use iterative elimination of weakly dominated strategies, just be aware that some arbitrariness is possible. Okay, that's just good to be aware of. Okay. Any other problems with iterative elimination of strongly or weakly dominated strategies? Are there any other problems? And now we're going to move into our next little topic. Okay, so remember the footloose example. This is a game of chicken. Okay. So again, in this chicken, if you both swerve, it's kind of like, okay. If you both don't swerve, that's a catastrophe. You both die. If I swerve and you don't, then you kind of win, and I get a little embarrassed. If I don't swerve and you swerve, then I win and you get embarrassed. Okay, this is a chicken game. Okay, let's see. How do I make a prediction using dominant strategies? So let's see. Is the case that for Ren, swerving dominates either strongly or weakly, not swerving? Okay, so does this dominate this? Well, 0 is less than 10. Okay, so no, it's not the case that this is always better than this. It's not like swerving is always better than not swerving. Okay, how about the other way around? Is not swerving always better than swerving? Well, let's see. 10 is bigger than 0, but minus 100 is less than minus 10. So that's not true either. It's not the case that not swerving is always better than swerving. Okay, so what we have is the fact that no strategies are strongly dominated. In other words, in this game, this chicken game, it's not like there's one strategy which is always better than the other. It's not like the prisoner's dilemma, in which case you never want to, pay taxes. You never want to bring the present. Okay. In this case, in chicken, it's not like swerving is always better than not swerving, or not swerving is always better than swerving. Right. If the other person swerves, you don't want to swerve. And the other person doesn't swerve, you want to swerve. So there's this kind of interdependence. It's not the case that one strategy is always bad. Okay. So in this case, no strategies are strongly dominated. Okay, so no strategies are weakly dominated either, right? Okay. So what do we do? Okay. We can make a prediction, and so then we have to think a little bit about what the next step is. We have to think maybe there's well, I guess we could just give up and say there's no way to make a prediction. But I think there is a way, so let's see if we can figure that out. Maybe we can make a prediction after all. And this is the way you start thinking about this. We first basically think about not deducing what people will play, but rather we make a prediction. That is, we think about all possible predictions, and then just see if those possible predictions make sense. So instead of deducing what people will play, just go ahead and make a prediction, and then see if it makes sense. Okay, so let's do that. How many predictions are there? Well, there are 4 possible ones. Okay. One is that they both swerve. This is one possible prediction that corresponds to this outcome here. Another one is when Wen swerves and Chuck doesn't. That corresponds to this one. Another one, of course, is when Ren doesn't and Chuck swerves. That's this one. And finally, of course, is if they both don't swerve. So there are 4 possible predictions. Okay. The idea here is that a prediction makes sense if, given the prediction, each person wants to play according to the prediction. Okay, so if I make a prediction and people want to play according to it, then it sort of makes sense. If I make a prediction and people do not want to play according to it, then the prediction itself is kind of not consistent. It's not valid. It doesn't make sense. People will want to move away from the prediction. So you're not going to make a prediction which people are going to want to move away from. Right? Okay, so let's see how that works. Again, there's 4 possible predictions. And let's just see whether it makes sense. So let's check. The first one is when Ren swerves and Chuck swerves, up here. Okay? Does it make sense? Does this prediction make sense in the sense that people want to play according to it? Okay, so this is the prediction. So Ren, we're going to predict they both swerve. Okay, so Ren realizes, so this prediction is made, we both realize this. I'm Ren, I say, okay, the game theorist is telling me that we're both going to swerve. If I'm Ren, do I want to play according to that prediction? Again, I'm Ren, I'm being told that we both will swerve. Do I want to play according to that? Well, the answer is no, because if I know that Chuck is going to swerve, okay, I'm Ren, the game theorist has told me that we're both going to swerve, I know Chuck's going to swerve, therefore I'm going to not swerve, right? 10 is better than 0, then if the game theorist gives me this prediction that we're both going to swerve, I'm not going to play according to that. I'm going to sort of deviate from it, right? Okay, so in that sense, this prediction, if we predict that both will swerve, that's not going to be stable. People are going to want to move away from that prediction. That prediction doesn't make sense. Okay, how about this one? This is where Ren swerves and Chuck doesn't. That's this one here. Okay, so if the game theorist makes this prediction, does anybody want to change from it? In other words, do people want to play according to the prediction once it's made? Okay, so this is the prediction. Okay, I'm Ren. I hear that the game theorist predicts that I'm going to swerve and that Chuck is not going to swerve. Chuck is going to go straight. Okay, so I'm Ren. Do I want to play according to that prediction? Okay, so again, the game theorist is telling me that Chuck is not going to swerve. Do I want to change? Well, if I changed, I would get minus 100. Okay, do I want that? No, I'd rather stay according to what the prediction is. So given the prediction, I, Ren, would like to play according to the prediction. How about Chuck? Chuck hears from the game theorist, oh, Ren is going to swerve and you're not going to. So Chuck thinks, okay, given what the game theorist told me, given the prediction, do I want to play according to that prediction? If I were to swerve, I would get 0 instead, right? So I don't want to change, right? I'm happy where I am. I'm getting my 10. Given the prediction, I do not want to change. I want to play according to the prediction. Okay, so given the prediction, neither person wants to change. Both people want to play according to the prediction. Okay, so in that sense, the prediction makes sense. Okay, it's valid in some sense. Okay. How about down here? This is the third prediction. This is where Ren doesn't swerve and Chuck swerves. We're in here. Given this prediction, does Ren want to change? If Ren changed, Ren would get a 0 instead of 10. So Ren, yes, does want to play according to the prediction. Okay. Given this prediction, does Chuck want to play according to it? Well, if Chuck were to do something different, he'd get a minus 100 and not minus 10. Okay. So again, given the prediction that Ren is not going to swerve, Chuck doesn't want to deviate. Chuck will still want to swerve. Okay, so given this prediction, both people want to play according to the prediction. No person wants to change. In that sense, the prediction is valid. Finally, we have Ren not swerving and Chuck not swerving. We're in this -100, -100 thing. Does anybody want to change? If we make this prediction, will anybody want to vary from it? Okay, so I'm Ren and I'm going straight. The game theory says the other person's going to go straight too. Do I want to play according to it? No. Okay, I'm getting a -100. I'm thinking, gee, I'm going to not swerve given that the other person is going straight, right? I want to deviate. I do not want to play according to what the game theorist has told me, so therefore the game theorist's prediction doesn't make sense. Okay? This is the idea. All right. Okay, so let's try to be real careful about what this idea is. So first I'll tell you what a strategy profile is. A strategy profile is a specification of what each person's strategy is. It's a possible prediction. In a two-person game, a strategy profile is a pair of strategies. So for example, these four things here, those are the strategy profiles in my simple chicken game. Okay. Here are the four strategy profiles. Okay. Okay. In a two-person game, a strategy profile is a pair of strategies. Okay, again, just go back. These are all possible pairs of strategies, right? In a three-person game, it's a triple of strategies, a specification for each person. Like in the Footloose example, there are four strategy profiles. We just talked about that. Okay, so we now know what a strategy profile is. Now this is our technical definition. We say a strategy profile is a Nash equilibrium, and this is named after a human being, John Nash. He's still alive. A strategy profile is a Nash equilibrium if no person wants to choose some other strategy, in other words, deviate, given what everyone else does. So a strategy profile is a Nash equilibrium if no person wants to choose some other strategy, given what everyone else does. Okay? A Nash equilibrium makes sense in that if it is predicted that everyone wants to follow the prediction, assuming it's true. So like we talked about, a prediction doesn't make sense is when you make a prediction, people don't want to follow it, then the prediction doesn't make sense, right? Nash equilibrium makes sense in that if it's predicted, then people want to follow it. Okay. Another way to say this is a Nash equilibrium is a self-fulfilling prophecy. It's a prophecy, once it's made, people will play according to the prophecy. Okay. So going back to our chicken game, this is one possibly Ren swerves and Chuck swerves. Okay, these are our four strategy profiles. Okay, first one is not a Nash equilibrium. Okay, this is 0, 0 here. Ren swerves and Chuck swerve. This is not a Nash equilibrium because given that we make this prediction, a person wants to deviate away from it. So for example, Ren would rather get 10 instead of 0. Okay. How about this guy here? Ren swerves, Chuck doesn't. That corresponds to this. This is a Nash equilibrium. This is a self-fulfilling prophecy. If we make this prediction, no one wants to deviate from it. If we're here, if I deviate, if Ren swerves, Ren deviates, Ren gets -100 than as opposed to -10. So he'd rather not deviate. Chuck is getting a 10. If Chuck were to deviate, he'd get a 0. So he doesn't want to deviate either. No one wants to deviate, hence it's a Nash equilibrium. Okay, how about this? This is the outcome where Ren doesn't and Chuck swerves. That's this. Okay, is this a Nash equilibrium? Well, Ren's getting 10. If he were to deviate, he gets 0. So he doesn't want to deviate. Chuck's getting -10. If he were to deviate, he'd get a -100. So he doesn't want to deviate either. So starting from this situation, from this prediction, no one wants to deviate away from it. So the name for that is, that's a Nash equilibrium. Finally, let's look at this one. If they're both down here, this is where neither person's swerving, they're both going straight. Does anybody want to deviate? And of course, yes. Ren is getting a -100. If he were to deviate, he'd get a -10. So therefore, this is not a stable situation. Okay, it's not a Nash equilibrium. Okay. What is the final prediction in this game? Well, we can say this is not going to happen. Okay, they're not going to both swerve, and also they're not going to both go straight. What we have left is these two possible strategy profiles. these are the two Nash equilibria. So these are the two Nash equilibria. Ren swerves and Chuck doesn't. Okay. Another one is that Ren does and Chuck swerves. Okay, so those are the two predictions. Does that make sense? Okay. This is our prediction. One person swerves and the other doesn't. So, like we said before, it's not going to be the case that both swerve, and it's not going to be the case that both go straight. Rather, we're going to say one person goes straight and the other person swerves. And you might say, well, how do I know who's going to swerve? And the answer is we don't. We will predict that one swerves and the other doesn't. We can't predict which person swerves. So these are two Nash equilibria. They're both reasonable predictions. Okay. Definitely this is not a reasonable one, and definitely this is not a reasonable one, right? Because if you were to make that prediction, people would not follow it, right? So these are at least reasonable in that sense. Okay, there are two possible Nash equilibria, so these are two possible predictions. Okay. Here's another example, arms race. Okay, this is just another version of our chicken game, right? In this case, US arm, so you can arm. If they both arm, it's bad. If I arm and you don't, that's good for me, not so good for you. Okay, and like if we both don't arm, that's like neutral. Okay, what are the Nash equilibria? Okay, let's just do step by step. Is this a Nash equilibrium? If I make this prediction, does anybody gain by deviating? Yes. The US will want to move away and get -5 instead of -10. So this is not a Nash equilibrium. How about this? Is this a Nash equilibrium? Does person 1, rather the US, gain from deviating? The US is getting 10. If we were to deviate, it would get 0, so the US doesn't gain. Soviet Union is getting -5. If the Soviet Union were to deviate, it would get -10, so it doesn't want to gain either. Right? It doesn't want to deviate either. So given this situation, no person gains by deviating, so therefore this is a Nash equilibrium. How about here? The US is getting -5. If the US were to deviate, it gets -10. Remember, the US is the red numbers, right? Okay. If it were to deviate, it gets -10, so it doesn't want to gain. It doesn't want to deviate. It doesn't gain by deviating. Soviet Union is getting 10. If we were to deviate, it would get 0, right? So the Soviet Union doesn't want to deviate either. From this situation, no one gains from deviating. So this is also a Nash equilibrium. Okay, so remember, this was not a Nash equilibrium. This is a Nash equilibrium. This is a Nash equilibrium. Finally, what about this one? Does anybody want to deviate? The answer is yes. The US would rather get 10 instead of 0, so this is not a Nash equilibrium. Okay, so in this game, which is exactly like the chicken game, there are two equilibria. This one, where the US arms and the Soviet Union doesn't, and this one where the US doesn't arm but the Soviet Union does. Kind of the interpretation is this. In an arms race, there will be a hegemon. So in other words, it's not like going to be like both people are armed because that's terrible. It's not going to be like no one arms because that's like a vacuum. Rather, somebody will arm, somebody will be the hegemon. We don't know who, but at least that's what we can predict. There will be a hegemon. And somebody will arm, the other person will be forced to back down. Okay. Another example, giving presents. This is back to our prisoner's dilemma. Okay. Remember, you can either give a present or not. The best thing is if I don't give a present but you give me one. Okay. Let's see, what are the Nash equilibria? Let's just check. Is this a Nash equilibrium where we both don't bring presents? If we're here, does anybody gain by deviating? Okay, right now Arnold's getting a 0. If he deviates, gets -1, so he doesn't gain. Beatrice is getting a 0. If she deviates, she gets -1. Okay, so nobody wants to deviate from here. So this is a Nash equilibrium. Okay, how about here? Who wants to deviate? Does anybody want to deviate? Okay, well, Arnold gets a 4. He doesn't want to deviate and get a 3, so he's happy. How about Beatrice? Well, if she deviates, she'll get a 0 instead of -1, so she wants to deviate. So in other words, if we were here, Beatrice will not put up with this, right? She'll want to deviate. This prediction doesn't make sense. This is not a Nash equilibrium. Not a Nash equilibrium. Okay, similarly, what's going down here? Does Arnold want to deviate? Right now he's getting -1. If he deviates, he gets 0, so he wants to deviate. This is not a Nash equilibrium. How about here? This is where they both give. Arnold's getting a 3, and Beatrice is getting a 3. Does anybody want to deviate? Oh yes, the fact is true. Arnold wants to deviate. Arnold wants to get a 4 instead of a 3. So this is also not a Nash equilibrium. This is not stable. People are going to want to move away from it. Okay, so in this example, there's only one Nash equilibrium where they both don't give. Okay? All other things, all other situations, all other predictions are predictions from which somebody will want to move away from. Okay? But once we're here, nobody wants to move away from this. Okay? Make sense? So note that, remember when we did this by dominated strategies, we also made the same prediction, right? If you think in terms of dominated strategies, not bringing a present always strongly dominates getting a present, right? 0 is bigger than -1, 4 is bigger than 3. Okay, similarly for bad trees. So the Nash equilibrium here makes the same prediction as iterative elimination of dominated strategies. So that's good. This is the same prediction that we got from eliminating strongly dominated strategies. Okay. This is my strictly ballroom example. Let's think about this again, just go step by step. Is this a Nash equilibrium where everyone claps? Well, Doug's getting 10. If he were to deviate, he'd get a 5. So he doesn't want to deviate. So he's happy. Rika and Yaya are getting a 10. If they were to deviate, they get a 5. So they're happy. So no one wants to deviate from this. So this is a Nash equilibrium. How about this? Is this a Nash equilibrium? Pardon me. Doug's getting a 5. If he deviated, he'd get a 0. So he doesn't want to deviate. However, Rico and Yaya want to, right? They'd want to get this 10 instead of 5. Since one person wants to deviate, it's not stable. Okay, this is not a Nash equilibrium. How about here? From here, Doug's getting a 5. Rico and Yaya are getting a -5. Does anybody want to deviate? Yes. Doug would want to deviate and get a 10 instead of a 5. Okay, this is not a stable prediction. This is not a Nash equilibrium. How about here? Doug's getting 0, Rico and Yaya is getting 0. Yeah, who wants to deviate? Doug, of course, wants to deviate. You get the 5 instead. Okay, so the only thing from which no one wants to deviate is this part here, 10, 10. So therefore, that's the only Nash equilibrium, okay, where they both clap. And notice, this is the same prediction as what we got from iterative elimination of dominated strategies, right? Remember when we did this earlier today, we said that Doug will always clap, right? Because clapping is always better than not clapping for Doug. Like 10 is bigger than 5, 5 is bigger than 0. So then we eliminate this one down here. And then given that Rico and Yaya, this 10 is bigger than 5, so we can eliminate this. So it's the same prediction from what we got before. Okay. How do I find all pure strategy Nash equilibria of a game? What you do is you check each profile, each little entry in the matrix, in the table. If some person can gain by deviating, given what everyone else does, then the strategy profile is not a Nash equilibrium. Okay? If any one person can gain by deviating, given what everyone else does, then it's not a Nash equilibrium. A Nash equilibrium is a strategy profile from which no one can gain by deviating. Okay, so you check each little cell and see, can anyone gain by deviating? If anyone can gain, then it's not a Nash equilibrium. Okay? A Nash equilibrium is a situation, a strategy profile from which no one can gain by deviating. Okay. Maybe I'll take a break and then I'll record the next one. Okay, thanks.